Transpose of the product of matrices. Hello everyone. To begin, let's recall that in our previous lessons, we have already examined how the transpose operation behaves when applied to scalar multiplication and the addition of matrices. Now, we are going to move forward and explore how the transpose operation interacts specifically with matrix multiplication. You will find that this property is quite unique compared to what we've seen so far, because it involves a fundamental change in the order of the matrices being multiplied. Due to this characteristic, this property is formally known as the reversal rule. Over the next few slides, we will examine exactly how this rule works and the mathematical reasoning behind it. Understanding the reversal rule. When you are finding the transpose of the product of two matrices, it is a common mistake to assume that the result is simply the product of their individual transposes kept in the same order. However, in matrix algebra, that is not how it works. Instead, the transpose of the product is equal to the product of the individual transposes, but they must be multiplied in the reverse order. Let's look at the formal mathematical statement for this rule. For any two matrices, A and B, provided that the product of A times B is defined, the transpose of the product of B is equal to B transpose times A transpose. To break this down further, the term AB transpose refers to the transpose of the matrix resulting from the product of A and B on the right side of the equation. B transpose is the transpose of matrix B, and A transpose is the transpose of matrix A. Now that we have introduced the concept of the reversal rule, let's take a closer look at how it actually works. Notice how A and B have swapped positions. In the next slide, we will discuss the mathematical reason why this reversal of order is absolutely necessary. Why is the order reversed? Now, you might be wondering why we cannot simply keep the matrices in their original order when applying the transpose. To understand the logic behind this reversal, let us examine the dimensions of the matrices involved. Let us assume we have a matrix A with dimensions m by n, and a matrix B with dimensions n by p. When we multiply these two, the resulting product matrix, a B, will have dimensions m by p consequently. When we take the transpose of this product, which we denote as a B prime, the rows and columns are swapped, resulting in a matrix with dimensions p by m. Now, let us look at what happens if we transpose the matrices individually before multiplying them. Matrix A prime would have dimensions n by m, and matrix B prime would have dimensions p by n. If we attempted to multiply these individual transposes in the original order, that is, A prime times B prime, we would be trying to multiply a n by m matrix by a p by n matrix. As you recall, matrix multiplication is only possible if the number of columns in the first matrix matches the number of rows in the second. In this case, the operation is mathematically impossible unless m equals p. However, if we reverse the order and multiply B prime by A prime, we are multiplying a p by n matrix by an n by m matrix. This is a valid operation, and the resulting matrix has dimensions p by m. This perfectly matches the dimensions of the transpose of the product that we calculated earlier. This dimensional requirement is the mathematical reason why the order must be reversed. To help you remember this rule more intuitively, we will now look at a simple real-world analogy. Real-world analogy, the socks and shoes principle. Now that we have analyzed the technical reasons regarding matrix dimensions, let us look at a simple real-world analogy to help you remember the reversal rule more intuitively. Think about the everyday process of getting dressed. In the morning, you follow a specific sequence. First, you put on your socks, and second, you put on your shoes. Now, if you want to reverse this entire process, which we can think of as the transpose of the action, you will find that you cannot simply reverse the individual steps in the same order. You cannot take off your socks first because your shoes are currently covering them. To successfully undo the process, you must reverse the order of the operations. First, you must take off your shoes, and only then can you take off your socks. Similarly, in matrix algebra, when we want to transpose a sequence of multiplications, we cannot simply transpose the matrices in their original order. Instead, we must apply the transpose operation to each matrix in the reverse order of the original multiplication. With this conceptual understanding in place, let us move forward to the next slide, where we will verify this property using a step-by-step numerical example. Step-by-step example. Now that we have discussed the theory and the socks and shoes analogy, let us put the reversal rule into practice. In this slide, we will verify that the transpose of the product of A and B is equal to the product of the transpose of B and the transpose of A. Let us start with our given matrices. Matrix A is a 2x2 matrix with the first row containing 1 and 2 and the second row containing 3 and 4. Matrix B is also a 2x2 matrix with the first row containing 5 and 6 and the second row containing 7 and 8. In step 1, we calculate the product of A and B. To do this, we multiply the rows of A by the columns of B. For the first element, we take 1 times 5 plus 2 times 7, which gives us 19. For the second element, 1 times 6 plus 2 times 8 gives us 22. Moving to the second row, 3 times 5 plus 4 times 7 gives us 43, and finally, 3 times 6 plus 4 times 8 gives us 50. So the product matrix of B consists of 19 and 22 in the first row, and 43 and 50 in the second row. Step 2 is to find the transpose of this product, denoted as the transpose of a B by interchanging the rows and columns. The first row becomes the first column, and the second row becomes the second column. This results in a matrix where the first row is 19 and 43, and the second row is 22 and 50. Now let us approach this from the other side. In step 3, we find the individual transposes of our original matrices. The transpose of A, written as a prime, becomes 1 and 3 in the first row and 2 and 4 in the second row. Similarly, the transpose of B, written as B prime, becomes 5 and 7 in the first row and 6 and 8 in the second row. In step 4, we calculate the product of these transposes. Remember the reversal rule we discussed earlier. We must multiply them in the reverse order, meaning B prime times a prime. Performing the multiplication, for the first element, we take 5 times 1 plus 7 times 2, which equals 19. For the second element, 5 times 3 plus 7 times 4 equals 43. For the third element, 6 times 1 plus 8 times 2 equals 22, and for the final element, 6 times 3 plus 8 times 4 equals 50. As a result, the product of B prime and a prime is a matrix with 19 and 43 in the first row, and 22 and 50 in the second row. In conclusion, if we compare our result from step 2 with our result from step 4, we can see they are identical. This confirms that the transpose of the product of B is indeed equal to the product of the transposes in reverse order, B prime a prime. Keep this reversal in mind, as we will see in the next slide why ignoring this order is one of the most common mistakes students make. Common mistakes. Now that we have seen the reversal rule in action through a concrete example, let's discuss some common pitfalls to ensure you don't make these mistakes in your exams. First, let's talk about ignoring the order of matrices. The most frequent error students make is writing that the transpose of the product of A and B is equal to the transpose of A times the transpose of B. If you recall our discussion on dimension analysis a few slides ago, multiplying the transpose of A by the transpose of B is often mathematically impossible because the inner dimensions will not match. Even in specific cases where the multiplication is actually possible, the resulting matrix will still not be equal to the transpose of the product of A and B. Secondly, it is very common to confuse this rule with the property for matrix addition. You might remember that the transpose of the sum of A and B is simply the transpose of A plus the transpose of B. The reason this is different is that matrix addition is commutative, meaning the order of the matrices does not change the result. However, as we have established, matrix multiplication is not commutative. Therefore, while you can simply distribute the transpose in addition, you must reverse the order of the matrices when dealing with a product. Key takeaways. First, remember that the property where the transpose of the product of A and B equals the product of the transpose of B, and the transpose of A is formally known as the reversal rule. As we have seen throughout the examples, the order of the matrices must be swapped whenever you distribute the transpose operation over a product. You cannot simply transpose them in their original order. This is a crucial point because, as we analyzed in our discussion on matrix dimensions, this reversal is exactly what ensures that the resulting matrix dimensions remain consistent and mathematically valid on both sides of the equation. Finally, it is important to note that this property is not limited to just two matrices. It extends to any number of matrices in a sequence. For instance, the transpose of the product of A, B, and C is equal to the product of their transposes in completely reverse order. The transpose of C, followed by the transpose of B, and finally the transpose of A. To wrap everything up, let's go over the key takeaways from this lesson.